welcome to the next portion, the last portion of this section under conic section, which is a hyperbola. So a hyperbola is essentially two ellipses gelled together. So you know that an ellipse over here is a parabola, apologies, it's a parabola, right? It can be like that or like that, right? Or it can be like that or like that, right? But for an hyperbola over here, there are only two kinds, right? What first kind is this, or the second kind is this, right? So it combines both into one picture. But the way that I like to actually study this, apologies, not ellipses, parabola. But the way that I like to actually remember this is not by remembering it as a parabola and then linking it to a hyperbola. The way I like to remember this is actually by remembering what an ellipse is and then linking it to a hyperbola, because of the way the general formula actually looks like. So to me personally, remembering it as an ellipse first, then linking it to a hyperbola is a lot more helpful. So let me explain. So an ellipse over here, okay, just writing out the formula again. So recap, an ellipse has a general formula of x minus h square over a square plus y minus k square over b square equals to 1, right? And depending on what the a value and the b value is, you can either get a very tall, skinny ellipse or a very wide, short ellipse, right? So let me just give an example over here. So let's say this over here is an ellipse. Here is the center of the ellipse, right? Here would be h comma k, and then the a values here, the a values here, the b values here, the b value is here, right? So that's the height and then there's the width. So translating this to a hyperbola, imagine I have an ellipse like that, and imagine I just cut the ellipse, I split it in half, right? Let's say I cut it. So when I cut it in half, what I end up with is I end up with this and this, right? And then from here, imagine if I flip them around. So when I flip them around, I get this or this, right? And then this one over here is now a hyperbola. Another way, or for the other case over here, imagine originally I have this ellipse over here, right? And then let's say I cut it like that, right? I cut it like that. From here, I end up with something that looks like that. 1, 2, right? And then over here, imagine if I flip them around, and I flip them around, I end up with this or this, right? And then now this one over here becomes a hyperbola. Therefore, I like to remember it this way because the hyperbola equation makes more sense when we actually think about an ellipse equation. So the hyperbola equation for the one on the left would just be x minus h square over a square minus y minus k square over b square equals to 1. So you can see that it's almost identical to the ellipse equation, right? The ellipse equation and the hyperbola equation, they are almost the same. The only difference is the negative. And personally in my head, I like to associate this negative with the flipping of it. So in my head is when I flip these two signs around, instead of adding them together, which is what the ellipse equation does, I subtract away from each other, and therefore they are both facing in the opposite direction. Okay, but with that said, right, the center is still here, right? This is still h comma k, and for this hyperbola there is two oblique asymptotes. Okay, just note this and this, right? These two are oblique asymptotes, which I will show you how to find the equation of later on. So just note that you must find the equation of, and I'll show you later down below. Okay, and then for the other case over here, the second hyperbola, now it's facing up and down. That means the general equation for this would be y minus k square over a square minus x minus h square over b square a square equals to 1. Right? Note that the center over here is still h comma k, but now, since it's facing up and down, you minus away the x squared instead, right? So the y actually comes first. And again, there are two different oblique asymptotes over here that you need to find out the equation of later on as well. Okay, so this is how I remember what a hyperbola is. And there are names associated with them specifically. These two over here, if you remember your compass, north-east, elephant, splashes, water, right? So you have north, south, east, west. So this one would be your, I'm just going to write it here, west-east hyperbola, right? Or some of you might call it the east-west opening hyperbola, right? Because this one opens in the east and then this one opens in the west, right? And then the other one will be your north-south. So you also can call this your north-south hyperbola, and that would be about it. Okay, that would be the naming convention of it. Okay, otherwise, take down these two general formulas and also the idea behind them, how we actually derive them from the ellipse, because this is not covered in most tutorial notes. And this is how it helped me intuitively remember it. Okay, if not, now come here, feel free to pause this video to attempt this question out. And when you're ready, you can come back to this video over here and carry on, and let's break down how we actually derive the graphs for this. Okay, let's break down how we actually sketch this tool, and most importantly, how we actually derive the equation of the asymptotes. Okay, if you didn't figure out yet, or if you don't understand what your school lecture notes actually mentioned about finding the equation of the asymptotes, this will show you how. Okay, let's start with 8. I have x squared over 4 minus y squared over 9 equals to 1. I'll rewrite this as x minus 0 squared over 2 squared, y minus 0 squared over 3 squared equals to 1. Right? And therefore, over here, I know that the center would be 0, 0. And then the distance over here, right? This hyperbola, since the x comes first, I know that this hyperbola opens sideways, right? So it opens this way and this way. In other words, this is an east-west hyperbola. And since this is an east-west hyperbola, my center would be here, 0, 0. And then this 2 over here, right? This 2 over here, not sure if I mentioned it earlier, but I'm just going to add it to the notes here. If this is an east-west hyperbola, the a square over here is very, very important because it tells us the distance over here. So from here to here, this will be a, and from here to here, this will be a as well, right? But for north-south hyperbola, then the distance from here to here, this will be b units, and from here to here, this will be b units as well. Okay, so back to here, right? From here to here, this will be 2 units, and from here to here, this will be 2 units. Then my hyperbola will extend until here, and it will extend until here, right here. Yeah, that would be how it basically looks like. And we know that my x-axis here, my y and my x-axis are over here. Okay, apologies. Yeah, so it'll be here like that. Make sure to draw your y-axis and your x-axis as well. So you have your curve from here, it goes down to here, and then comes back here. Then from here, it comes back here, and then down to here. Right? So that would be the east-west hyperbola. But again, that's not the end, because now we need to find out what is the equation of this asymptote and this equation of this asymptote. And I'm going to show you how. So first thing we do is that we make y the subject. I'll have y squared over 9 equals to x squared over 4 minus 1. Right? Now, as x approaches plus minus infinity, since we know that this is an oblique asymptote, right? This negative 1 over here, or this minus 1, in this context, minus 1 becomes negligible, right? As x becomes very, very huge, that effect of that minus 1 becomes negligible. So we can say that y squared over 9, the behavior, tends towards x squared over 4. It tends towards it. Like, so whatever value x squared over 4 tends towards, that is the value that y squared over 4 will actually tend towards, right? So that means from here, we get that y squared will tend towards 9 over 4 x squared, right? And then if we bring the square root over to the other side, then over here we'll derive that y tends towards plus minus root 9 over 4 x squared, which means that y over here will tend towards 3 over 2x, or y will tend towards negative 3 over 2x, right? So that's how we actually derive the two equations of the two oblique asymptotes. The two oblique asymptotes are y equals to 3 over 2x, or y is negative 3 over 2x. So here we have y equals to negative 3 over 2x, y equals to 3 over 2x over here. Okay, and this step over here is very, very important, right? Identifying that the effect of negative 1 becomes negligible as x approaches infinity, and therefore the whole behavior of the y value tends towards only x squared. And that's how we actually derive this when we remove the square root. Alright, so that will be all for A, and that is the final sketch for this. So I'm going to be going through B now, but feel free to pause this video now to take out any notes that you have before we actually jump right into B. Okay, so let's go through the second example over here. And what we have over here is y plus 1 square minus 25, x minus 2 square equals to 25. Okay, first thing I realize is that I have a y square, I have x square, and I have a minus sign over here. So immediately once I see these three things, right, immediately in my head I'll be thinking, okay, this is definitely a hyperbola. And once I see these three things and think it's a hyperbola, I'll immediately recall what the general formula of a hyperbola is, right? I'll get this b square, then over here I'll minus x minus k square over a square equals to 1, right? I will get this. So I know that I have to make this to 1 to match the general formula. And therefore I will divide the 25 over to the left hand side first. So I'll have this divided by 25 minus, then the 25 will cancel this one out, so it's just this over 1 equals to 1, right? And therefore I end up with y plus 1 square over 5 square minus x minus 2 square over 1 equals to 1. So from here we can tell a few things, right? The center would be negative 1 comma 2, and this, since the y comes first, this will be a north-south hyperbola, right? The ones that open upwards, and the distance from the center to here, right? This distance over here would be 5 units. Same thing for the center to here, this also will be 5 units as well. So with that said, we are able to now sketch this accurately. So I pull this out, yx, and over here we have the center being here, right? The center is negative 1 comma 2, so that would mean that it should be, let's see, it should be around here, right? Negative 1 comma 2 over here, that will be the center. And then go up by 5 units, so here to here this is 5 units, and here to here this is 5 units. So my hyperbola should be from here to here, and then from here to here, right? Just extend this line, this, and extend this line, and then this will be the y, right? So we have two different hyperbolas over here. Now we need to figure out what are the oblique asymptote equations once again, right? So how do we exactly do that? We will use the same method as before. So I'm just going to bring this here. I'll have y plus 1 square minus 25, x minus 2 square equals to 25. So I'll bring this over, equals to 25 x minus 2 square plus 25. And then we'll say that as x approaches plus minus infinity, the y value will tend towards 25x minus 2 squared, right? This one over here, this plus 25 becomes negligible. I mean, you don't have to write negligible in your working. You can just say that it tends towards this value, and that'll be fine already, right? Because by writing it this way, you're actually implying the above. So we will say that y plus 1 actually tends towards square root of 25x minus 2 squared, right? Plus minus, of course. So y plus 1 will tends towards plus minus 5 bracket x minus 2. Which means that y will tend towards negative 1 plus minus 5 x minus 2. And then from here, we get two oblique asymptotes, right? We get that y will tend towards negative 1 minus 5 bracket x minus 2, or y will tend towards negative 1 plus 5 bracket x minus 2. And in the end, over here, this one, I'm just going to write it this way, we end up that y will tend towards minus 5x plus 10 minus 5x plus 9. 5x minus 11. Yeah, that makes sense. So with that said, your graph will look something like that. So we have one that shoots up here, and then one that shoots down here. Oh yeah, apologies. I realized that I made a small mistake here. Here is supposed to be 2 comma negative 1, right? I'm wrote in the opposite positions. So I'm just going to readjust this to come here instead. Yeah, then that will make more sense, right? 2 comma negative 1. And then from here, it will shoot up by 5 units. It will shoot down by 5 units. And then overall, the graph will look something like this now. Okay, let me just circle this. I'll just bring this up slightly. Maybe I make this a bit shorter, right? And then I make this a bit shorter, and then this should be able to fit. So like that, right? And then I end up with 2 asymptotes. So I'm just going to draw the big asymptotes in purple. 1, 2, right? And then this one is y equals to negative 5x plus 9. This is y equals to 5x minus 11. So that will make more sense in this context over here, right? Whereby here the y-intercept is minus 11, and then the y-intercept here is 9. Okay, so overall, this is how we sketch the two hyperbola curves. Let me know if you've got any other questions. Apologies for the mix-up earlier on. And that's it. Any other questions, please text me personally or leave your comments below. If not, I'll see you in the next video for the next concept. Thank you.